Extensional geological provinces like the North Sea have been intensively explored for oil and gas. In 1993, half of the world's production of hydrocarbons came from extensional traps. The extensional faulted block is probably the most common structure in sedimentary basins, and the crests of tilted blocks constitute promising targets. Entrapment is generally controlled by tilted strata, faults, and unconformity on top of the pre-rift units. What are the geometrical and mechanical rules for the occurrence of these traps? What is the three-dimensional geometry of the fault pattern? To understand the extensional mechanisms, we did a series of sandbox experiments analyzed by X-ray tomography, examining the complete evolution of normal faults and investigating the three-dimensional geometry of structures. The sandbox experiments were carried out in the acquisition field of a medical X-ray scanner so as to visualize cross-sections of the model during deformation. Before looking at normal fault modeling in detail, let's look at the extensional tectonics modes, starting with the mechanical aspects of extensional faulting. The state of stress in a given point is shown by an ellipsoid which corresponds to the locus of stress vector's extremities. In water, the state of stress is isotropic, each stress vector being equal in all directions. But in solid sediments, the state of stress becomes anisotropic, and vertical stress is greater than horizontal. The stress ellipsoid is defined by three principal axes. The maximum principal stress, sigma 1, is vertical. It's approximately 3 times greater than the two horizontal stresses, sigma 2 and sigma 3. The state of stress is plotted in the tau sigma plane. Tau is the tangential stress component parallel to the potential fault plane. Sigma is the normal component perpendicular to the fault plane. Brittle rocks with a Coulomb behavior are defined by two failure limit lines. Their dip angle, phi, is the internal friction angle. The limit lines separate a stable domain from a failure domain. The state of stress in a Moore diagram. In water, the three principal stresses are equal. The state of stress is represented by a single point on the sigma axis. In rocks, the vertical principal stress, sigma 1, is larger than the two equivalent horizontal stresses, sigma 2 and sigma 3. The state of stress is represented by a circle here. If one of the horizontal principal stresses is reduced by horizontal extension, the three principal stresses differ. 3 circles represent the state of stress. A very small reduction of one of the horizontal stresses is sufficient to reach the limit lines. Then the rock fails, inducing extensional faulting. How can we reduce the horizontal stress? Several modes of extension have been proposed. Locally and on a small scale, reduction of horizontal stress and extension may occur at the crest of anticlines or at the crest of diapiers. On a much larger scale, extension may be produced by gravitational collapse of mountain belts when compressional forces vanish, as in the Basin and Range province. Extension of the brittle upper crust may be produced when divergent forces occur deep within the upper mantle. This is the mechanism generally invoked to explain the development of continental rifts like the Rhine-Graben. Along continental margins, very low-angle slope at the base or even at the top of a sedimentary pile can induce gravity sliding and extensional faults. In the Gulf Coast area, where sedimentation rates are quite high, evaporitic layers and overpressured shales constitute favorable detachments over which large listric normal faults develop by pure gravity. The analog experiments were focused on gravitational faulting. However, most of the structures on the gravitational models also apply to other modes of extension on various scales, the outcrop or brittle crust scale. To simulate the viscous behavior of the weak décollement layer corresponding to salt, overpressured shales or ductile lower crust, we used silicon putty, which has a viscosity of 10 to the power of 4 pascals second. At low strain, this material shows a Newtonian behavior, its strength being proportional to the strain rate. To simulate the brittle behavior of the sediments, we used dry sand and Pyrex powder with a grain size of about 100 microns. Laboratory failure tests at very low confining pressure measure an internal friction angle of 32 degrees for the sand and 41 degrees for the Pyrex powder. The models were prepared in a simple wooden box. The bottom of the box is covered with a layer of silicon, and border effect is avoided by coating two sides with silicon as well. Then various layers of sand and Pyrex powder simulating the brittle strata are leveled. The square grid is for controlling the surface view deformation. The box is slightly tilted to increase the gravitational effect. One side of the box is removed and the model deforms by gravity alone. Deformation can be watched in tomographic section on the scanner monitor. In the absence of sedimentation, faulted blocks are poorly tilted and Horst and Graben systems are horizontally translated over the silicon layer. Note that the silicon rises at the base of the Graben. If, however, we deposit new strata during gravity sliding, the resulting geometry is quite different. The first faults are very closely spaced, but only a few of them propagate to the newly deposited layers. Close to the free boundary, listric faults and tilted blocks develop, while antithetic faults and more symmetric grabens appear in the center of the model. We performed a series of experiments to test the effect of changing the thickness of the ductile layer. The resulting geometries are quite distinct. The thicker the silicon, the wider the area of deformation. Fault vergence is also controlled by the thickness of the silicon. Mainly synthetic faults occur when the silicon layer is thin. Mainly antithetic faults develop in the model with the thickest silicon layer, while more symmetric grabens appear in the intermediate model. The initial thickness of the sand also affects the fault geometry. In the 3 centimetre thick sand cake, 3 domains are clearly defined. A synthetic domain where listric faults dip towards the slope, a symmetric domain characterized by simple grabens, and an antithetic domain where symmetric initial grabens evolve in asymmetric tilted blocks. In the 5 centimetre thick experiment, the whole model was in the slope domain. Initially planar faults become listric, and tilt angle can reach 45 degrees. How is it possible to accommodate block tilting along faults? In the case of circular faults, there's no volume problem and blocks can easily rotate. In a listric fault, differential tilting is accommodated by a rollover and a crestal collapse graben in the hanging wall block. In several of the experiments, tilting along planar faults was accommodated by conjugate faults in the foot wall. Note the upward migration of the ductile silicon in the footwall block faulted zone. The crest of the footwall block is often cut by an imbricate extensional fan which develops as tilt increases. Early faults with low dip become inactive while new highly dipping faults occur. Weak layers in the sedimentary pile can induce refraction of the normal faults and fault disconnection. In this experiment, we introduced a 2 mm thick silicon bed which produced fault refraction and independent fault sets. We saw the development of faults in gravitational gliding systems in 2 dimensions along cross-sections parallel to the transport direction. The 3-dimensional geometry of the deformed model can be analyzed from surface views or from the top of the silicon layer. It can also be analyzed from serial cross-sections. Structures are not cylindrical, and faults are not continuous through the entire model. These serial cross-sections clearly show how we pass from a system of 5 tilted blocks on one side to only 3 major tilted blocks on the other. Horizontal cross-sections demonstrate the spoon shape of listric faults and the three-dimensional pattern of their intersection. These models, based on simple mechanical concepts, are used as research tools to understand the mechanisms of extension. They also constitute a valuable template for the interpretation of seismic profiles in various extensional basins, such as rifts and passive margins where large amounts of hydrocarbons have been generated.